Right, in this video I want to go through closing gap for the unit data representation. It's a topic we did recently, and I wanted to go through every single question and ensure that all of us are scoring full marks. We start with question one. Question one is units of measurement. So we've got a single nibble. A single nibble is going to be four bits. A single bite is 2 nibbles, so that's going to be 8 bits. Next, we've got permutation. So this is how many values you can have, or possible values you can have with different number of bits. If it's 1 bit, we can have a 1 or a 0. If it's 2 bits, we can have 4. If it's 3, it's 8, and so on. So it's pretty much the base, which is 2, and then to the power of, in this case, 4. So that would be 16 values. Then we have 2 to the power of 7. So that's 2 multiplied by 2 7 times. So that would be 128. What number base is binary? So we know that binary is base 2. And we know that it has a 1 and a 0. Hexadecimal is base 16, and it uses 0 to 9 and A to F. Tick 2 boxes to show the statements that are true about hexadecimal. Hexadecimal can represent a greater range of numbers than binary. No, it can't, because hex has to be converted into binary. Hexadecimal is easier for people to read than binary. It certainly is, because it's using letters. So it'll be B. Hexadecimal is faster for a company to process than binary. No, it's not. Hexadecimal is more accurate than binary. It's not, because it still has to be converted into binary. Hexadecimal takes less space in RAM. No, it doesn't. Hexadecimal takes less time to type. Yeah, of course, because if you're typing a letter such as A, that's going to be far quicker than writing that in binary form. Which statement best describes what computers represent using binary? So all data are represented using binary. All data and instructions are represented using binary. Some data or some instructions. So it's going to be B. It's not just all data, but it's also instructions. Complete the table below, converting the numbers across the different number system. The first row is in binary, the middle is hex, and the last is decimal. So what we need to do for this, if we're converting this into, so the first column is binary, middle is hex, last is decimal. So to get decimal, we could make a table here. So we could do a small table here. 1, 2, 4, 8, 16, 30, 32, 64 and 128, and we're trying to get 80, so to get 80 we need 64. Oh no, ignore that. So what we're doing here is 80s in hex. We're trying to convert that into decimal. What might be more useful is actually if we do the binary version of that. So if you do 8421, 8421, we'll try and make 8. You need a 1 to make an 8. And for the 0, we don't need to use any of the headings, so we can just keep that 0. So that actually is the binary version of 80 hex using 8421, because there's 2 hex digits. Each one is a nibble, 4 bits. So now we've got the binary, we can just put those underneath here. So 1 and the rest are all zeros. So that tells me that this is equal to 128. So that row is done. Next row we've got 1, 2, 3, 4. So we put a line in between. So we've got 128 plus 64 plus 32. So that's already we know is 224. And we've got to convert this into hex. Well, to do that, we just do 8421, 8421. We've got 111 and 0, and the rest is all 0. So 8 and 4 is 12. 12 plus 2 is 14. 14 is E, and that one is 0. So that's E0. 255. That's in a decimal. This is going to be in hex, and that's going to be in binary. Well, in binary it's going to be all 1, all of the ones, because that will give you 255. And in hex, well, if we break that down to 8421, 8421, that's going to be F, because the first 4 bits are F, which is 15, and then the second nibble, if it's all ones, that's going to be F as well. So F and F. A1, so A is 10, so it's going to be 1, 0, 1, 0, 1, 0, and 1 is going to be 0, 0, 0, and 1. So how did I get that number? Well, I got that number by doing 8, by doing 8, let's draw again. So in here we would do 8, 4, 2, 1, 8, 4, 2, 1. We're trying to make A. A is 10, so you need an 8 and a 2. So that's the first nibble done, or the first digit done. Then we do the 1. To make a 1, you don't need an 8, you don't need a 4, you don't need a 2, you need a 1. And in terms of what this would be as a value, well, you'd have to make your table again. 128, 64, 32, 60, 16, 8, 4, 2, and 1. So that's 1, 0, 1, 0, and then 3 zeros and 1. So 128 plus 32, that's 130, 160, and then the 1, so that's going to be 161. That's the answer. Place the following terms in order of size. So we've got to look at what the order would be for this particular example. So if we look here, bit is the smallest one, so we'd start with bit. So that one's done. Kilobyte, terabyte, gigabyte. Okay, so terabyte. Before terabyte it's going to be gigabyte, so that one is done. Gigabyte's done here. Before gigabyte it's going to be megabyte. Before megabyte you've got so we've done that one. Bit, after bit is going to be byte. Oh, actually no, it will be nibble. Then it's going to be byte. Well, this drawing tablet is awful. Apologies. Why is it doing that? Wow, that is... Yeah, so bit, nibble, byte, and then kilobyte. Apologies for this. I think I need to maybe update some of the drivers, perhaps. Okay, so bit, nibble, byte, kilobyte, megabyte, gigabyte, terabyte, that's fine. So how many bytes are there in a kilobyte? So 8 bits is 1 byte, so the answer you're looking for is 1000. You can put 1000 or 1024. How many bits are there in a kilobyte? So if we know that 8 bits we get a byte and 1000 bytes make a kilobyte, so it's 1000 times by 8. So the answer would be 8000. Convert the following values that represent file sizes into bits and show you working out. So for 8 kilobyte, we need to get the working out into bits, so we do 8 times 1000. So that's going to give us 8000 bytes, and we're going to multiply that by 8 to get bits, so it's going to be 64,000. Next one is 5 meg, so we're going to do 5 times that by 1000 to get kilobytes, so that's going to be 5000 kilobytes. Then you're going to multiply that by 1000 to get bytes, so that would be 5 million. And then 5 million, we're going to multiply that by 8, so we should get 40 million bits. Add the following 8-bit binary number together. So the rules are the following. So 0 and 0 is going to be 0. 0 and 1 is going to be 1. 1 and 1 is going to be 1, 0. So 1 and 1 is going to be, whoa. 1 and 1 is going to be 1, 0, and then 1 plus 1 plus 1 is going to be 1, 1. So 1 plus 1, 0, carry the 1. 0 plus 1 is 1, 1 plus 1 is 0, carry the 1. Bring that 1 down, bring that 1 down. That's going to be 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0. So 0, 1, 2, 3, 4, 5 ones, and double 0. Scrolling down, same method really, it just looks a little bit more trickier, but it's the same, exact same approach. So we've got 0, 0, so that's going to be 1. 1 and 1, that's going to be 0, plus 1 is 1. 1 and 1 was 0, you had a carry for that one. 1 and 1 is 0, carry the 1, that will be 0. 1 and 1 is 0, carry the 1. 0 plus 1 is 1. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 0 plus 1 is 1, and then we've got triple 1. So if we've got triple 1, it's going to be 1, carry the 1. If we've got triple 1 again, it's going to be 1, carry the 1. And if we've got triple 1, it's going to be 1, carry the 1 again. So the answer should be 1, 2, 3, 4 ones. 6 ones. 1, 0, 1, 1, 1, 0, 1, 1, yeah. Did we make a slight mistake here? Just have a level check. So that would be 1. 1 plus 1 is 0, carry the 1. 0 plus 1 is 1. 1 plus 1 is 0, carry the 1. 0 plus 0 is 0, yeah. 1 plus 1 is 0, carry the 1. 0 plus 1 is 1. Then we've got 4 ones. 1 plus 1 is 0, carry the 1. 0 plus 1 is 1. 1 plus 1, that one is 0. Carry the 1. And then 1 plus 1 is 0, carry the 1, 0 plus 1 is 1, 1 plus 1 is 0, carry the 1, 0 plus 1 is 1, 1 plus 1 is 0, carry the 1, 0 plus 1 is 1, bring the 1. Yeah, so that should be 1, 2, 3, 4 ones, a 0, and that, yeah, that's correct. 4C, so we're completing a left shift of 2 on the binary number. So every time we go to the left, what will happen to that particular value is that it will multiply by 2 and every time we go to the right, it's dividing by 2. So in this particular case, so that one will be times by 2, and every time to the right, it's divided by 2. So there's a couple of approaches you can take in doing this. So one approach is you can find out what this value is. So this one we've got 1, 2, 4, 8 and 16. So 8 plus 16, which is 24. 24 plus 2, which is 26, plus 1, so that's 27. 27 doubled once is 54. Doubled again is 108. So what we can do with this is we can make 108, or we can actually shift the numbers. So if you've got here, we've got 3 zeros and then we've got 1 1. So if these two digits move to the left twice, it'll be 0 1 1. So it'll be 0 1 1, and then 0 1 1. And in this bit, there's nothing here. You just pad it with zeros. We can check what this number is. 64 and 32 is 96. 96 and 8 is 104. 104 plus 4 is 108. So this we know is the correct answer. Here we've got another number. So 1, 2, 4, 8, 16, 32, 64, 98. 64 and 128 is 192. 1, 2, 4, so that's 200. So if it's 200, it's moving to the right twice. So that's going to be 100. It's halving. Then it's going to be 50. So we just got to represent 50. Another thing you can do is if it's moving to the right twice, you start with 2 zeros, because in here it starts with 2 ones. So you put 0. Then you just put those numbers 1 1, and then 0 1 0, 2 0, 1 and 0. And you can check what this value is. So 1, 2, 4, 8, 16, 32, 64. Oh, it's not. And 128. So that's 32 plus 16 is 48. 40 plus 2 is 50. Yeah, there you go. That's the correct answer. What is the binary effect of a number shifting 4 places to the left? Well, if you shift a number 4 places to the left, every time you shift in that particular number, you are doubling it. So if we, for example, in here shift 1 place, that's multiplying by 2, by 4, by 8, and by 16. So times by 16. That's what will happen with the number. It will be multiplied by 16. A text file has 126 characters and was created using ASCII. How many bits will the size be? Well, ASCII is 7 bits, so it's going to be 126 times by 7, which will give you around 882 bits. Here we've got an ASCII table, so the letter A is 65, so we've got to find out what the letter C would be. So if A is 65, B is 66, C is 67. So C is going to be 0, 1, and then 1, 2, 3, 4 zeros, and then 1, 1, because it's 64 plus 2, which is 66, plus 1, which is 67. And E is going to be 0, 1, and then 3 zeros, and then 1, 0, 1. So that's 64 plus 4, 68, plus 1, 69. Which statement describes a character set? So a list of characters defining the access rights to a computer network? No. A list of characters controlling the execute? No. A list of characters mapped to a unique binary code? Perhaps. A list of characters representing memory locations? So it's not memory locations, it's a list of characters that uniquely bind. So they're used to this. A character set is used to display the characters within a system. State the binary value of the ASCII character A from here. So if we look at this, that's a C, that's A, and that's T. So the A would just be that. 2 zeros, 1, 2, 3, 4, 1. Next one, S. Well, we've got T, and then S is after T, and we just find out what that one is. Once we know what one particular character is, we can then find out what the other character would be in this particular example. So state the binary value for S. So here, if we look 1, 2, 4, 8, 16, 32, 64, 32 and 2, 4, 8, 16, 30, 64 plus 32 plus 16. So that's 96, 112, and then 1, 2, 4, 116. So then what we need to do is one more, so 117. So 117 would be so you need 64, 32, so that's 96, 112, 116, 117. So it's going to be 117 for that particular example. So that's going to be 111, 0, 1, or 1. Just need to double check, is that right? So 1, 2, 4, 8, 16, 32, 64. So it's 64 plus 32, 96, plus 16 is 112, 1, 2, 4 is 116, and we're making 117, 96, 112, 116, 117. Yeah, that would be the right answer. (5F) Which two statements about ASCII and Unicode are false? So Unicode is an alternate character set to ASCII. That is true. Unicode represents a wider range of characters than ASCII. That is true, because it can represent other languages and special symbols and emojis. Unicode can represent characters from more than one language. Yeah. So Unicode uses fewer bits to represent each character than ASCII. No, it actually uses more characters because it's 16 bits, UTF-16 or 32. All of the ASCII codes are different to Unicode codes. That's false as well. So the answer for this one would be D is false. And D. Define a pixel. I think I'm going to try and type this one. And we can say a pixel is single point in an image. We could also say a single point of color. State the number of pixels in the image in figure 2. So the pixel is width times by height. So the number of pixels is 10 columns going across times by 8 rows going down, so it's 80 pixels. State the minimum color depth required to represent each pixel in figure 2. So if we look at that particular example, we've got two colors, black and white, so we need just one bit, and that will give us two colors. Calculate the resolution for the image. The resolution is the width times by height, so that's going to be 8 times by 10, and that's going to be 80 as the resolution. Describe what metadata is and give an example of data you would find within it. So metadata is data about data. i.e. a file. You can say that an example of this would be the file size, file type, location, resolution, etc. Figure 3 shows a different bitmap that uses 3 colors. It also shows a 10 by 8 bitmap image. Calculate the minimum file size that would be required to store the bitmap image in figure 3. Give your answer in bytes, show your workings. So what we're going to do for this particular example is we're going to look at the number of pixels across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10, which is the width. Multiply that by 1, 2, 3, 4, 5, 6, 7, 8. 10 times 8. So that's going to be 80. And then we're going to look at the number of bits we use for the color. So we can see white, black, and gray. So there's about 3 colors there. So we need to multiply that by 2. So that's 160 bits. We want the answer in bytes. So we've got to divide that by 8. So the answer is going to be 20. So that's 20 bytes. Analog sound must be converted to a digital form for storage and processing in a computer. Define the term sample resolution. So sample resolution is the number of bits per sample. State one disadvantage of a high sample resolution. Well, we know that an advantage of it is going to be a better quality sound, but a disadvantage is going to be a larger file size because you're storing more data. We also know that it will take longer to transmit. We could say that it uses more memory as well because the file size is bigger. A 50-second sound has been recorded at a sample rate of 40,000 Hertz. 2 bytes have been used to store each sample of the sound. Calculate the file size. So what we need is 50, which is the seconds. So we need 50 times by 40,000 times by 16. Because we need to turn it into bits. So the marks that are allocated are what you do with this next. So if we use a calculator quickly for this, so we've got, to save time, 50 times 40, 2 million times by 16. That's going to be 32 million here. So that's in bits. We've got to divide that by 8 to get to bytes. So that's going to give us 4 billion bytes. And then 4 billion, we've got to divide by 1,000 to get KB. So that's going to give us 4,000. And we divide it by 1,000 to go from KB. So that one was bytes there. That one is bits. So 4,000 divided by 1,000, that will give us 4. So the answer is 4 megabytes. Here we've got a black and white image has been compressed using Roland encoding. The first bit in each of the bit pattern represents the color. So you can see in this one that would be the color. So 1, 2, 3, 4, 5, 6, 7, 8. That will also be the color. And then the image has a run of 60. So 1, 2, 4, 8, 16, 32. 32 and 16 is 48. 56. So that's 60. So that would be this bit here. And then this one is 30, which is obviously these values there. So if it's 60, then that means that that is 60 is black. So that would be black there. And then 1 is representing white. So using our RLE method, give the bit pattern for a black and white image that has a run of 64 white pixels followed by a run of 15 black pixels. So 1, 2, 3, 4, 5, 6, 7, 8. So that's halfway. we know that white is 1, so we need to do 64 white, so that's 1, and then that one is the 64 column, the rest are going to be 0. So if you imagine in the 128 we're using that for the color, all 0, so that doesn't get used. So the next heading that gets used is 64. It goes all the way to 164, 32, 16, 8, 4, 2 and 1. And in here again the 128 doesn't get used because that's for the color. So we've done 1, we know that's white, so we need to do black, 0, and the black color we're representing is 15, and I know 15 is literally the first 4, 1, 2, 4 and 8, 12, 14, 15, the rest can be zeros, and that should be our answer. Here we've got Huffman. State the string that the bit pattern represents above. So every time we go to the left it's a 0, every time we go to the right it's a 1, so that would be 0, that would be 1, that would be 0, that would be 1. So if we look at this, 0, 0, okay, so that'd be A, because we can't do 000, because if we do 0, 0 and 0 we end up here and there's no value here, so that's A, so that one is done. Then we've got 0, 1, 0, 1, so that's D, so we've done that. Then we've got 0, 1 again, that's D again, so we need to take that off. Then we've got 1, 0, 1, 0, so that's E, so that's done. And then we've got 0, 1, 0, 1, so add it. That'll give us the 2 marks. The table below shows the Huffman codes for the characters in the string H, E, S, E, and so on. We can see that the frequency of the character is 20. We can see the letters here, and we can see the Huffman code. Show your workings to calculate this particular example. So, lots of ways of doing this. One thing we can do is look at the frequency and look at how many bits we use. So I might do it here and then, because that will be a bit easier to do. So we've got 6 as the frequency and the number of bits we use, so we just multiply that together. So that would be 12. 5 times 2, that would be 10. 4 times 2, that would be 8. 3 times 3, that would be 9. 2. So 2 is the frequency, so that letter A appears twice, and every time it appears we're using 3 bits, so that's going to be 6. So if we add this, that's 22, 30, 39, 45. So 45 is uncompressed. So that's uncompressed. And it says, state how many bits would be saved if the string was encoded using Huffman. So if it was, 45 is compressed, not uncompressed. 45 is compressed. So uncompressed would be 20 letters times by 7, because ASCII 7, extended ASCII is 8. So that's 140 bits, and that's uncompressed. So 140 bits uncompressed, just here. Wow. And then 45 we've got compressed, so if we take that off, that will give us 95. So we're saving 95 bits. So the answer would be 95 bits, that's what we're saving. What's the difference between lossy and lossless? Well, we know lossy will permanently delete the data. So lossy compression will permanently delete data. You cannot restore back to the original. Lossless will enable you to restore the image restore the data without losing anything permanently. That's usually enough. But other stuff you can say is, if you wanted to, lossless is ideal for text, and lossy is ideal for images, sound and videos, because even if things are lost, the quality is not affected too much, and your brain will fill in the gaps for that. Hopefully that makes sense and it's been useful. So just go through, identify the gaps, and we'll try and address them in future lessons as well as Unit 6s. Thank you for taking the time to go through this particular paper, and I'm hoping to do more videos like this, because I think if we go through them, there's a better structure, there will be less problems with this, and I'll try and sort the issue with the tablet out as well. So then all of us can aim for 80-90%, which will hit that grade 8.